I promise, though, I'm going to try to avoid, I think I've got 2 equations and I've got 1 number. So at least from an engineering point of view, that's good. This thing started off, the presentation at one point was going to be on river rehabilitation, and hence the front slide, but it's more about stormwater management than river rehabilitation. That's what it did look like, and a year down the line, that's what it could be made or was made to look like at Morocco. Whether this is sustainable in the absence of proper catchment management, anybody knows, because the catchment is trying the runoff is trying to dig itself a donga, but we did try there. Why we would, very briefly, why we might want to manage stormwater. Then a little bit about doing it right, planning, design, building and maintenance of stormwater drainage systems, stormwater management systems. Talk then, in order to know what we're trying to achieve, we have to know what problems we're trying to address. So I'll talk a little bit about the impacts of urbanization, and then principles of stormwater management, and finally, what's probably of most interest to everybody is the techniques for managing stormwater. Some of them, not all of them by any means. All right, why might we want to manage stormwater? The obvious reasons are we want to avoid this sort of situation where the water gets out of hand and washes people's gardens and things away. This is an eroded donga just downstream of Vorna Valley. That's the Vorna Valley Spruit. It used to be a lovely rural catchment of Midrand. It's now an urban catchment of Midrand. Hence, the wetland that was up at this level no longer exists. And that's a bridge in the south of Johannesburg. In all of those issues, too much water in one go, too much water over a long period of time, and too much gunk in the water are really the issues that we are trying to address in stormwater management. But in order to manage this stuff, we really need to do it right. So what do we want to avoid, first of all? We want to try to avoid this kind of concrete line channel, despite the beautiful stonework that was done in the 1920s and 1930s, really good work. Ideally, we'd like to build it, to knock it down and use that stonework in some sort of, or those stones in some other sort of building. Here, somebody's attempt at fixing a donga. What do you do when you have dongas to fix? You stick gabions in them. So, but in this instance, they stuck gabions down the one side, forgot that rivers erode on both banks, and also tried to go a bit deeper. So we have a gabion wall, a lovely little concrete channel, and the river flows, or the stream flows down the bottom of it. So, how was this fixed? That's at the bottom of Santon Drive, where Santon Drive joins William Nicol. It was Santon Parks. It wasn't Joburg City Parks. It was Santon Parks. They planted some trees along the side so you couldn't see it from the road. And then they put a picket fence, which is now covered in bugweed, and now you definitely can't see it from the road. These guys decided that the Braamfontein Spruit was sort of public property, so they may as well have as much of it as they can. So, well, let's build a house hanging over the side of the river. It's not great for stormwater management. It's not great for flood management. It's not great for riparian corridor functionality. It's not great for anything else. I think it's also a part of stormwater management. I hope the owner of that house isn't here, or maybe I hope he is here, or she is here. And then this is a technical thing. Why do you think the person who designed this fancy outlet with this tiny little pipe at the bottom really and truly believed that it had to have such a big mouth? I'm not sure, but do it right. And if you're going to build it, also build it right and try to make sure that it stays there. You really don't want this to happen. Down on the Braamfontein Spruit below Pirates, that was a Loffelstein wall that didn't have a proper foundation, so the Loffelsteins are now going to Hartbeespoort Dam slowly. This view is looking downstream in a culvert. I'll talk about where you start stormwater management and stormwater drainage facilities, but you don't actually build a great big one and then hope that the water is going to find its way into a little culvert at the bottom. It doesn't work too well. This is looking downstream in a stormwater pipe that somebody got their planning wrong, or maybe they didn't. They just came afterwards and decided they needed an electrical conduit through the stormwater drain. So we have this clean, great stormwater pipe and a box. So that pipe doesn't work too well either. If you're going to canalize rivers, you really do need to do something about maintaining them. So scour holes are not great because they end up in bank failure, and that costs maintenance. And this finally, this is quite an interesting problem. That is a thin-walled plastic pipe. It's a structural walled plastic pipe. It comes in a roll, and as you want to make a pipe, you actually roll the thing out and it clips together, the little edge like that, and you end up with turning your plastic strip into a pipe. But it's got an effective structural thickness of about 8 millimeters of plastic. Now, somebody took a 900 pipe and they buried it under 2 meters of soil, and they thought because somebody told them something, it was going to work. When I say do it right, it doesn't only mean build it right. What I mean is also manage it correctly. What happened here, the consulting engineer had designed a concrete pipe. Concrete pipes are expensive. The contractor went along to the developer and said, I've got a much cheaper plan. I can do it with this cheap plastic pipe. And the developer said, well, if it works, of course, let's do it. So the consulting engineer was overridden. And this plastic pipe, I don't know whether you can see the top there. It's just quietly collapsing to itself. Consulting engineer was the first line of attack. You let us build this thing. Guys, everybody needs to be sensible about what they're doing. So this kind of mistake can be quite embarrassing. But what are we trying to achieve? We're trying to manage the impacts of urbanization on stormwater, the effects of that they have on the catchment. What does urbanization really do? First of all, we know you get an increase in imperviousness. Everybody knows that. We've got roofs, we've got driveways, we've got roads, we've got parking areas, and the rainwater that hits those surfaces runs off in a hurry. Nothing goes into the ground, and we have this increase in runoff. In order to accommodate that extra runoff, what do? We build efficient drainage systems, which speeds the water up even more. So what that does then, that makes this, because the system is more efficient, it responds to shorter, more intense storms, and you get this sort of vicious circle. The more efficient storms, or more intense storms you have to deal with, the more efficient systems you have to build. And so your systems are perpetually becoming undersized. Similarly, then we have to canalize our water courses because we've got increased runoff and the water courses are being damaged. Again, what it does is it makes the system that much more efficient. And then the hard one, soil compaction. We say, but we've got open spaces we've got gardens, we've allowed for these median islands in roads. And why aren't they working? Why aren't they absorbing the water? It's actually quite simple. A natural soil is not a homogeneous mass. It's got voids, it's got macropores, which were animal burrows, which were old root channels and things like that. Not root canals, that's a bit painful. Yeah. And those soils have an amazing capacity to absorb water. But when we build anything, the first thing we do generally is we go and we clear the site and we compact this, and then we go and plant something afterwards. That changes the structure of the soil and it reduces its permeability by probably a half, probably even more than that. So just by providing open spaces within our developments doesn't necessarily mean that the soil has the capacity to absorb the water. You need to help that. Reduction in the surface area of vegetation cover. Okay, reduction in the surface area of vegetation cover. Leaves take an enormous amount of rainfall to wet them. You can't do, by taking the vegetation out, you increase the runoff. Encroachment onto the floodways, of course, we're taking the storage out of the system. What do these all do? They hasten the runoff and they reduce temporary storage and they reduce the infiltration into the soil. And then some quality effects of the urbanization. We increase the point and diffuse pollution sources. The failure of the wastewater drainage systems, we've all seen it. We've all seen the popped sewers all over the place. Poor and non-existent sanitary facilities. You know, probably the grossest thing that I've seen in a long time is the sanitation system in Khayelitsha. They tried to build a vacuum sewer system and it doesn't work. But for whatever reasons, it doesn't work. So the sanitation system there consists of paint tins and checkers bags, plastic bags. In each one of the little shacks is a paint tin and a checkers bag that gets used for the night. In the morning, the bag gets tied up and it gets tossed out with the garbage put next to the skips. And of course, it gets picked up by the stormwater drainage and down it goes into the rivers. Impacts of this: increased frequency of runoff. Why is frequency of runoff an issue? We know that we can have wetlands sitting on very, very steep slopes in rural catchments, 3%, 5%. I've seen wetlands probably sitting on a 10% or more slope on the side of the hill in Etala. The reason that they can exist is because there's the runoff, surface runoff over those areas occurs very seldom, maybe once a year, maybe once in every couple of years. And so in between those surface runoff events, the vegetation has time to reestablish. It might be damaged, there might be a bit of erosion, but in a year or two, the vegetation is reestablished. What do we have when we have impervious surfaces and it rains? 2 millimeters of rain is all it takes to start runoff from a road. So every single time it rains, boom, the river gets hit. Hydrograph comes down, the vegetation hasn't a hope. So increased frequency of runoff is probably one of the worst, most insidious causes of damage in urban drainage systems. Increased peak flood and increased volumes speak for themselves. Rapid and extreme variations have huge impact on the ecology of systems. Temperature variations in the salmonid streams in particular, that's where it's been researched, but I'm sure if we'll see temperature variations if our fish populations are ever researched. Increased sediment runoff and deposition. We heard yesterday that I think sediment runoff from construction sites is about 100 to 500 times more than from natural catchments. Deterioration of the biological and aesthetic quality of water, increased debris load in runoff water. We see that, and I showed you a picture of that. And of course, the reduction in groundwater recharge. All of these things come together as a set of symptoms and result in a thing called the urban stream syndrome. The urban stream syndrome, the deterioration of a watercourse. I showed you that one picture of the river at Vorna Valley suffering from exactly that. All right, some consequences that we feel in society. There's an increased hazard. Every summer we see drowning we hear of people who drown mainly because of a lack of appreciation of the increase in or the power of the water. A lack of appreciation of how quickly the water level can rise in a river. Increased flood hazards speak for themselves. Exposure of new developments of flood hazard speaks for itself. Loss of function and stability of hydraulic structure speaks for themselves. Threat of dams, blockage and failures, all of those things speak for themselves, so we won't go into them. More consequences though. Loss of a recreational amenity of water courses. People are not really interested in dangling their feet over the edge of a 3-meter high vertical sided donga. So they write them off. We see increased public health risks. Even where we create water bodies, people will come into contact with that water, and you can't really stop them. So if you create a water body, somebody's going to swim in it. This is a little, an urban stream in an urban lake in Soweto. I hate to think what's in that water, but the kids are quite happy playing in there. If we're going to create water bodies that people have access to, we have an obligation to make sure that those people are safe in those water bodies. And the result of that, of course, people lose an appreciation of the water courses and water bodies, and if they lose an appreciation, they're no longer interested in maintaining them, and again, we have this vicious circle. If you're not interested, if you can't maintain a stream that works, then why should we be interested in it? And if we're not interested in it, why should we pay you to try to maintain the stream that in a state that works? So what do? We use SQIDS, and we stick to the principles. The principles, and I'd like to go through these quite quickly because some of them are quite important. Understand that the drainage is a regional phenomenon. It doesn't respect boundaries. It doesn't respect political boundaries. It doesn't respect property boundaries. The only thing that water knows about is running downhill. Right? Every urban drainage area has two systems, whether they were designed or not. We have a pipe system or some sort of little stormwater management system, and then we have the floodways. Water will find its way downhill, whether it has to go through somebody's lounge to do it, it will find its way downhill. Runoff routing is a space allocation problem. You need to allocate space to water. Water has a volume. You can't compress it. You can't do anything with it. You've got to let it flow down the hill. Right. And don't rely on transmitting the problem downstream. It was the old engineering way of doing things. Put it in a pipe, get it to the river as fast as possible. It'll go away. So what do? We use, as I said, we use SQIDS. SQIDS, SQUIDS, BMPs, LIDs, WSUDs. You hear all of these things. You hear in a meeting, we're going to use SQIDS. And somebody says, well, SQIDS are so last year, we're going to use SQIDS, or we've got a brand new SQUID. They all mean basically the same thing, unless you're an American, in which case you use best management practices, far superior to SQIDS, SQUIDS, or anything else. But they're all the same stuff, and really and truly within small parameters. So what kind of SQIDS, what is the purpose of a SQID? Really, all we're trying to do is we're trying to recreate the natural processes. Infiltration, we're trying to give the water opportunities to infiltrate into the soil, and that reduces the volume of runoff, and it reduces the peak discharges as well. We're trying to recreate, give the water opportunities to evaporate, so we're trying to recreate evapotranspiration areas, planted areas and things. We want to store the water, so we create storage, detention facilities, retention facilities, and that reduces the peak discharge. Can, in certain instances, reduce the volume of runoff as well. We're looking for water quality, so to improve the water quality. So we want to trap some of the sediment. We might want to filter out some of the finer material as well, and we want to expose the water to bacterial activity and plant activity to take out some of the nutrients and possibly some of the heavy metals as well. So we have bioremediation facilities, and they work as a treatment train. First of all, let's try to prevent the runoff. So let's try to reduce soil compaction in our open areas, and let's try to have as many open areas and disconnected from the drainage system as possible. That prevents runoff. Then source control. Let's try to store the water on the roofs of buildings if at all possible. The roof of a building is an amazing storage opportunity. The design, I told you I've got another number for you. The normal design, structural design load for an accessible roof is 2 kilonewtons per square meter, which corresponds to 0.2 of a meter of water. 24-hour, 50-year rainfall over most of this country is 0.15 of a meter of water. So if you store the water on the roof of your building, you can store the whole rainfall for 24 hours that would occur once in 50 years. We ignore that, but it's there. If we can't control the flow runoff at source, we try to control the runoff on the site. And if we can't control it on the site, then some cities maybe have regional stormwater management, stormwater runoff control facilities. The idea is to address multiple impacts in a single facility. So if you can address quality, if you can address runoff volume, if you can address peak flow, all in the same facility, that's great. And of course, there are very, very many options, ways of doing this. Stick to the standards first and foremost. There are standards for stormwater management, and you need to stick to those. Engineers will tell you you can't move away. We've all heard that. Engineers are the boogie people. First of all, the safety standard. Be aware of the power of flowing water. Water flowing at 3 meters a second. Now that's a fast, pretty much, it's sort of a jogging pace. Has a wave height of 0.5 meter. So if you have a stream of water which is flowing ankle deep, that deep, and it can easily be flowing at ankle deep, and it's flowing at 3 meters a second, when you step in it, the wave hits you on your hip. And if it hits you on your hip, you're probably going to roll over, fall over, and then you will roll down the water course. How fast? Now, 3 meters a second is slow for water. 5 meters a second, engineers will tell you, is reasonably safe, and people say, well, 5 meters a second is being unrealistic in terms of the cross-sectional area. Let's jack it up to 5 or to 7 meters a second or whatever. How fast can a man run? The fastest man in the world can run at 10 meters a second. How fast do you think you can run in the rain over rough ground trying to rescue somebody who's fallen in a stormwater drain? Maybe half of that. You can't. Safety is a huge issue. Other standards, local authority objectives, try to keep the post-development peak discharge equal to the pre-development peak discharge. That's what the city of Johannesburg has, their standard is. The city of Cape Town is trying, going a step further and saying, not only do we keep the discharge the same, the peak discharge, but we also try to keep the quality, the post-development quality the same as the pre-development quality. Storage, Q in is equal to Q out minus change of storage. That's the equation I was going to give you. Rainwater harvesting. You can harvest rainwater very successfully. You're entitled to harvest rainwater according to the Water Act. It specifically says you can, right? Be careful of it. Quality can be quality of rainwater is generally quite good. It's a little bit acid because it's in equilibrium with the carbon dioxide, but it's not too severe. Be careful if you're retrofitting old buildings, because they used to use a lead primer on the galvanized roofs. You don't really want to feed too many kids lead. It's bad for their brains. Okay. The yield, you can go into this. There's lots of references. Storage, I spoke about flat roofs, green roofs. I'll show you some pictures of green roofs and how they work. That's the Science Museum, the new Science Museum in San Francisco. This is a domestic house. This is age-old cottages in the Faroe Islands, so don't believe that green roofs are a new thing. They've been around for ever since ever. And a university campus somewhere in Japan. They're superb. They recreate the natural runoff conditions. Retention storage, you keep the water in a place for a long time, you lose volume by infiltration into the ground in evapotranspiration. You get water quality improvement by exposure to bacterial activity and the uptake of nutrients. You get sequestration of phosphate in the soils as well. And of course, as you guys are much more interested in this thing called visual diversity. Lots of opportunities for visual diversity in retention storage systems. Swales, bioswales, that's a very functional bioswale. Again, you're meeting the benefits of the requirements of trying to recreate a natural system. Debris screen. Okay, sorry guys. I just wanted to tell you about this opportunity very, very quickly. Instead of having a curb inlet which goes straight into a pipe, build a curb inlet that goes into a tree bowl. Put some stones in the top 300 millimeters of your tree bowl, and then take the excess water into the pipe. The first couple of millimeters of water will go to irrigating your tree. You'll get benefits in the biofiltration, bioretention in the tree bowl. It works very well, and it can work as urban furniture as well. Infiltration, just some infiltration at whatever scale you like. That's a regional infiltration point in Australia. This is the bottom of Neil Armitage's garden. This is my own garden with a little infiltration facility next to the front door. And this is what happens if you try to infiltrate stormwater next to a foundation on collapsing soils. You break your house. So you can't use the same system for each thing. There's no panacea. You've got to choose what's appropriate for the site. Constructed wetlands, really good idea. Same sort of principle. Permeable paving, great idea. Just by way of interest, you have a permeable storage layer and then some sort of separation fabric if you're not brave, and a bedding layer for the paving, and then some sort of block with capacity for water to flow in. Most of these things can take rainfall intensity at around about 300 to 500 millimeters an hour, which is faster, lot more rapid than any rainstorm that we experience. Will you take? If you're interested in references, you can take those down. All right. No.
Thanks so much, Chris.